My name is Dhar Al-Shhoumi, and we're going to continue on question 3 of this quiz that was given to us by our amazing teacher. So for this topic, we're going to cover optimization. This question is a classic optimization question from IB Math, and we're going to find the dimensions of a rectangle that gives the largest possible area using only 3 sides of fencing, and I'll be explaining everything step by step, so you could answer this question with ease. So firstly, we have to read the question and understand the question. The following diagram shows a rectangle, area A, B, C, D, enclosed on 3 sides by 60 meters of fencing, and on the 4th by a wall AB. So we're given a rectangular area ABCD. One side AB is against the wall, so we don't need fencing there. The other 3 sides BC, CD, and DA are enclosed using 60 meters of fencing. We're asked to find the width of the rectangle that gives its maximum area, and find the maximum area of this rectangle. So first off, we have to understand the question. We are building a rectangle using 60 meters of fencing, but only 3 sides are fenced because the wall covers 1 side. So we want to maximize the area of this rectangle using the fencing wisely. This is called optimization. We're choosing the best possible value, the maximum area, based on only 60 meters of fencing. Now we have to define the variable. We can label the width as x and the length, which is along the wall, y. So we have two vertical sides, which we can say x plus x, which will give us 2x, and one horizontal side, which is y. And the total fencing used is 2x plus y is equal to 60. And y equal to 60 because it says the 3 sides has 60 meters of fencing. Now we want to maximize the area of the rectangle. The area of a rectangle is A is equal to width times length, and in regards to this question it is x times y. But right now we have 2 variables, x and y, and we want to write everything in terms of just 1 variable. So it's easier for us to differentiate. So from what's given, we can let y to be alone, which is y equals to 60 minus 2x, and we plug the formula, which is the length times width, is equal to x times 60 minus 2x, which will give us 60x minus 2x. Now this is our objective function. It represents the area in terms of x. Now we have to differentiate to find the maximum. So to find the value of x, which will give us the maximum area, we take the derivative of the area function and solve when it equals to 0. So we start with a is equal to 60x minus 2x, and to differentiate that, we're going to do this 60 minus 4x. Almost forgot here because you have to anyways, what you do here is the x just goes, it cancels, and the 2 here multiplies with the 2 because we're going through the formula. Minus 1 should become 4x, just 4x, and we're going to set this equal to 0. So 60 minus 4x is equal to 0. Take 4x to the other side, divide 4, and this should tell us that the optimal width of the rectangle is 15 meters. Now to find the maximum area, we know that x is equal to 15. We can find the maximum area by plugging into the formula we already had, which is A is equal to 60 x minus 2x squared. Now substitute 15 into the x's. Which will equal to 900 minus 450, and that will give us 450. Now that's how you could find the answer. Don't forget meter squared. That's how you solve a question easily. And just a quick recap to what I've done. We defined the variables x and y to describe the rectangle and write the formulas. We used 2x plus y to limit the possible values for the sides, and we wrote a is equal to x times 60 minus 2x to express area with one variable, and we differentiated 60 minus 4x to find when the area is at its maximum, and we solved and made it equal to 0 to find the width of the maximum area, and plugged what we got here into the formula, and we got 450, which is the actual maximum area, and that should be our answer. Now tips to remember for optimization: we have to always label variables clearly. We have to know the formula, one formula, what you want to maximize. The other formula that you could use is this, judged by what you're given. Replace one variable using the replace one variable, which is what happened? Replace one variable, take the derivative and set it equals to 0, just what I did here, to find the maximum or minimum, and always double check by plugging your value back into the area formula. And that's how you solve a three-sided fencing optimization problem. It's a question that could pop up in your IB exam, and I hope this is helpful enough. Thank you.